Okay, let's start class. Last week, we talked about the chapter 1, which is an introductory chapter. We discussed two types of distributions, binomial and multinomials. And of course, the Bernoulli is the special case. And we talked about how to have a point estimate of the parameter through the MLEs. And how do we do the hypothesis test to the distribution parameters. We can have three different tests: log, like ratio test, word test, and a score test. And we have three corresponding confidence intervals based on these three tests. So this is the chapter 1. So now we will start to talk about the chapter 2. So the chapter 2, we will focus on the table, contingency table. Okay. So this is the outline. So we will first just start with the basic sampling distribution. Then we will talk about some key attributes for these sampling designs. And then we will talk about some commonly used measure for the association between two categorical variables. Okay. And then we will talk about some invariance properties and the inference. Okay, so for the table, contingency table. A contingency table is a joint frequency distribution. Like in this example, right? We have the column variable has two levels, no pneumonia, pneumonia. And the rows has two levels, no vitamin C and vitamin C group. Okay, so we have four numbers. It's a 2x2 table. So why we say the contingency table is a joint frequency distribution. So what does joint mean? The joint distribution in statistics, we know that it is related to more than one variables, right? So for this number like n11, it's not just depend on one variable. It also depends on another variable. Okay, so the n11 is the number of frequency for the no pneumonia and no vitamin C. So you see, it depends on two variables value. So that's joint. So what is the opposite of joint? It's called marginal, right? So the marginal is what? Like these numbers are the marginal. These numbers are the marginal. So marginal means it only depends on one variable. Okay, so what is n1 plus? 1 plus in the subscript, okay? So that means the total number of no vitamin C. So it only depends on the vitamin C status. And N2 plus, it's the vitamin C group. And similarly, N plus 1, that's no pneumonia. N plus 2 is the number of subjects has pneumonia, right? So these are the marginals, okay? And this is what? This is a total, okay? So if we only talk about the distribution for these margins, then it's the marginal distribution, right? If we talk about the numbers from M1 to M22, so this is a joint frequency distribution. See that? Okay, so these are very basic concepts. And but it doesn't have to be 2 by 2. It can be more general. Let's say X has I categories, Y has J categories. Okay, so this can be not 2 by 2, but I by J. So we can have X, maybe, let's say this is the row variable, and Y is the column variable. So we have J, or we have I rows and the J columns. Okay, so that's the more general definition for the contingency tables. Okay, two-way. Okay, and we can also have three-way, but three-way we have to be represented through the multiple two-way tables. Okay. Okay, so we are interested in relationship between the variables, right? So here, for this case, we want to see if taking the vitamin C is associated with the pneumonia status or not. In other words, if the subject, if people take 500 milligrams or more vitamin C daily, will they have less chance to get pneumonia? Right? So this is actually testing the association between these two categorical variables, if they are associated or not. And if it's associated, what kind of association it is? Positive, negative, or what? Right? So these are very practical questions that we can answer through the test. Okay, so sometimes we can have the X is the explanatory variable and the Y is the response variable, like regressions. Okay, and we can have a certain order, like X is the explanatory, Y is the response. But sometimes we don't have to. We can just say X and Y, they are both explanatory variables, or these are just two variables. And then a question is when we should have, let's say we have two variables, when we should have one of them to be response variable, one to be explained, or when we should just consider these two as two variables, right? So these are the questions which you need to think about. Because if you ignore that, and that may give you the wrong model. Okay. And also knowing this can help you to understand more about statistics. So in what case, when we should consider one of the variable as a response. Okay. So that really depends. For example, if we want to have a predictive model, okay, so we want to use one variable to predict the value of another variable. Of course, in this situation, we should have one of them to be response. And the one that we want to predict it is the response, right? The other one should be the explanatory. And there are other cases we can also have a response. For example, if we know that one of the variable is the cause, one of the other variable is the effect. So there's a cause-effect relationship. So in that case, we should have the one that is the cause as the explanatory variable. The other one is the response variable, right? And if two variables, one variable happens before having the outcome for the other variable, so there's a time difference. Okay, so x that comes first, y comes later. Then in that case, we should have. It's okay to have the y as a response, x as a explanatory variable, right? And also in some experiment design, okay, if one factor is what we controlled, another factor is actually what we measured, then in that case, the one that we controlled is the x. The one that we measured is the response, right? So you can see, I'm just telling you some situations that you should consider, have one of them to be the response, one of them to be the explanatory. If all these situations doesn't apply, then probably you may just treat both variables as the same. So just consider these two variables as two variables. You don't have to assign one of them to be response. Okay. Okay. This is the probability structure for the contingency table. So here, what are these pi's? Pi 1, 1 through pi ij. So these are the joint probability. I've already explained what does the joint mean, right? So that means is the probability of having the x, which is the row variable for the ice level, and y, which is the column variable at j's level. So that's the joint probability for the x at the ice level, y at the j's level. Okay, how do we estimate it? We can estimate it through the Nij, that's the counts at the ith row, j's column, divided by the total counts, n. Okay, and the notation is pi ij. And you may ask, why? What's the difference between this pij and pi ij? Are they the same? So take a look. Which one is the Greek letter? Right? Of course, this one is the Greek letter. And I said, in statistics, the tradition is what? Think about parameter and statistic. Which one using the Greek letter? The Greek letter gives to the parameters. Okay, so that means this is the parameter, which is the true value fixed but unknown. But this is the statistic based on a data set, so which is random but known, right? Okay, so you should know this. Okay, and marginal probability. I've already explained what is marginal. Px equals to I, so that's the marginal probability for the rho variable at I level. So that's we can estimate it through using the Pi plus. Why is a plus? Plus means it's summation through all the columns at I. Okay, that's the Ni plus divided by N. And Ni plus is the row sum, okay, for the ith row, divided by the total number, okay? And we can also write the parameter as pi I plus, which is equal to the summation for the pi ij, summation over all the j's. That means over all the columns for the ith row, okay? And similarly, we can have the p y equals to j, okay? Okay, the next one is conditional probability. We've already seen this last time, right? So the conditional probability, what is conditional probability? Like this one, the first one is conditioned on the x level at I, okay? And the probability of getting the y at j. The probability can be estimated through the Nij divided by the row sum, right? Ni plus, okay? So these are the probability structures for the contingency tables. Okay? So for the contingency tables, you can see we have joint probability, marginal probability, and the conditional probability. So make sure you understand these. Okay? And the interpretation is different, right? And we will see some examples. Okay? So this one is the belief in afterlife example. So we have the row variable as gender. Column variable is the belief in afterlife or not. Okay? So the total sum is 1,127. And these are the observed numbers. Okay, so the P11 is 509 divided by 1,127. And we got 0.45. What does that tell us? So this is the estimate for what? For the joint probability, right? So that tells us the probability, so the proportion of female that believes in afterlife and believe in afterlife is 45% in this population. Okay, so that means 45%, about 45% of the people in this population are females and they believe in afterlife. So that's a joint problem. Female and believing afterlife. And the P22 is for the males who do not or undecided believe in the afterlife. Okay, so that's 9%. So both Pi11 or P11 and P22 are the joint probability. The third one, what is the proportion of subject believe in afterlife. So this is marginal. This one is marginal because it doesn't relate it to the gender. It doesn't say female or male. So that only depends on the subject believing afterlife. So that's the marginal. So then we should look at 907, right? That's the number of subjects believing afterlife divided by the total. So 907 divided by 1127. That's the proportion of subject believing after. Okay. This one for female. What is the proportion of subjects believe in afterlife? So that is conditional probability. So given the gender is, so for this one is the conditional probability, right? So believe, so given it's female, right? The condition on the subject is female, and the probability of the proportion that believes in afterlife. So that's the conditional probability. How do we estimate? So then we should just look at the first row, right? And we have 509 females believing afterlife out of 625. So this should be the 509 divided by 625. So that's the conditional probability. And what about males? Then we should look at the second row. So we have 398 over 502. So that's the proportion for the males that believes in afterlife. Okay, so this is a good example to illustrate these three probabilities: joint, marginal, and the conditional. Okay. Okay. So a question: can we always use the Nij divided by N to estimate the pi ij? So can we always use this one to estimate the joint probability pi ij? Not always, sometimes. Okay, so here just give you some example. So for the fixed row sums, suppose X are the row variables, refers to different groups like the treatment and placebos. Okay, and then we are we have the two-arm study of occurrence of an adverse event, A, AE. So AE is yes or no. So this one means having the adverse event. This one, no adverse event. Okay, for the treatment and placebo. And of course, this is a two-arm study. We have the equal number of subjects in the treatment and placebo. Okay, so can we just use 5 divided by 100? Say the probability or the proportion of the subjects that have the adverse event and in the treatment group is 5%. No, we cannot say that because in this study, we are actually fixing the row sums. Okay. So in that case, what probabilities can we estimate? Okay, so the joint probability we cannot estimate properly because here we are fixing the row sums. Okay, so what we can estimate it is what? Is the conditional probability. And the conditional probability has two types, conditioned on the X or conditioned on the Y. So here is what? So conditioned on the groups, conditioned on the X here. Okay, so given, so within the treatment group, okay, we have 10% of the subjects have the adverse event. But for the placebo group, within the placebo group, we have 38% of the subjects that have the adverse event. Is that right? That we can say because we are fixing the row sums. So we have to do, so we can only estimate well through for the conditional probability condition on the X bar. Okay? And can we estimate the marginal probabilities? Let's say the marginal probability for the treatment is 50%. That is meaningless because that is preset. We don't have to estimate. That is controlled. So this is a controlled experiment, right? And can we estimate also the marginal probability for the uh, for having the adverse event is 48% or is 24% out of 100? No, we cannot estimate because we fixing the row. Okay, so in this study, if we fixing the number of subjects in the treatment and placebo, we can only estimate well on the conditional probability for each row. Okay. Okay. Then what is the distribution for the numbers of having the adverse events for the treatment group? So let's say for the treatment group, okay, we have five subjects have adverse event out of 50. Okay, so what is the distribution for the number of subjects that have adverse event? This should be what? Should be binomial, is that right? What is the number of trials? We have 50 trials. What is the number of success? Let's define the success as having the adverse event. Okay, so then we have 5. So you see, that's the binomial. Why it's binomial? Because the binomial needs to have, so here, each subject that having the adverse event is independent, right? And identical. So that's a binomial trial. Okay, so this distribution is the binomial distribution. Okay. Okay, for the sampling design, we can have the fixed rows sums just as this one, we can fix the row sums, 50, 50, okay? Sometimes we can have the fixed column sum design, okay? So we can have the column sum to be predetermined, okay? And sometimes we can have a fixed total sample size. So we are not fixing the row sum, we are not fixing the column sums, but we are fixing this, okay? And you may ask why we need to care about these different sampling designs, right? Because different types of sampling designs is related to different distributions. And also different sampling designs tell us, only allow us to estimate some specific probabilities. Okay, so like the fixed row sum, as I said, we can only estimate the conditional probability given the row value. And the fixed column is the only estimate the conditional probability for the x given the y. Y is the column variable, okay? So here the x is the row variable, y is the column, okay? So for the both the fixing the row and the columns, okay, the distribution that we should use is the multinomial or binomial, depends on the number of groups, okay? So here for fixing the row sums, then within each row, the distribution of y follows a multinomial or binomial. Okay, so for the binomial, just like this is binomial, right? For the multinomial means if we have more than 2 levels, then it will follow a multinomial, okay? And for the fixed column sums, then the conditional probability of x is the row variable, at each column follows a multinomial or binomial, okay? But for the fixing the total sample size n, then this follows a multinomial distribution with I times j categories. Okay, so this one multinomial with I category. This one multinomial for j category. Okay, and the last one is if everything is random, n11, n12, m21, n22, marginals are random, even the total is random. That's also possible. So in that case, it's not a multinomial anymore. Then it's a Poisson distribution, which we will see in the next slide. Okay, so you can see different sampling designs is related to different distributions and different probabilities, so you should know that. Okay, so make sure you can correctly identify the sampling designs, and that is the first step to conduct the statistical analysis. Okay, so what is Poisson process? So Poisson distribution is a very useful distribution for the count data. Okay, so you can see the Poisson distribution. That it covers from 0, 1, 2, 3, until infinity. All the integers start from 0. So Poisson process can be used to model the events happening randomly in the space or the times. Okay, and the Poisson process has a very special property that is the independent increments. So what does that mean? That means so that means let's say these examples. So the calls coming in for an emergency numbers. Okay, let's say we have 5 calls coming in this time intervals. And in the next time intervals, the numbers of calls that we received is independent with the number of calls that I received before. So they are all independent. So that's the independent increments. Okay. And also the Poisson process has a property that for a small interval, time interval, or small space area regions, the chance of having 2 or more events is negligible. So that has to be a small. Okay, and the chance of an event roughly proportional to the size of the regions and intervals. Okay, so these are the properties for the Poisson process. And the probability of observing X event in a region of size T is this one. So that's the exponential to the negative lambda T times lambda T to the power of X divided by X factorial. Okay, so what is the lambda T? Okay, so T is the size, and the lambda is the expected number of events that happen in a unit. Okay, for example, the number of car accidents in a region, the number of car accident happens within a week for a particular region. Okay, so let's say this one is following a Poisson process, right? And the expected number of car accidents that happens within a week, let's say, is 3. Okay, so the lambda is 3. Okay, now I want to know what is the number of car accidents that happens in a month. Okay, in this region. Okay, so here the lambda is in per week, right? So the unit is per week. Now we want to go to the months. Okay, so let's say we just say 4 weeks in a month. Okay, that's approximately 4 weeks in a month. So then the T will be what? T will be equals to 4 because the T is the size. We have 4 weeks. So then the number, so the probability of observing X car accidents in this region over a month is what? Is e to the lambda is 3 times 4. Okay, so that's e to the negative 12 times 12 to the power of X divided by the X factorial. And that is the probability of having the X car accident within months. Okay? Okay. Now, let the Nij be the cell counts in the IJ's classification. So when the total sample size N is random, okay? So that means when this total sum is random, okay? Then we say these Nij's follows a Poisson distribution, okay? And the Poisson sampling assumes the Nij is following a Poisson with mu ij. Mu ij is the parameter. So for a Poisson distribution, the notation is, so here we have lambda t. So that is useful when we have some size t. But sometimes if we just have just one size, we always use weekly, no monthly. So then we can just change it to the mu, okay? So in other words, in this formula, mu is what? Mu is lambda times t, okay? That's it. So if we don't need to worry about the size, just use the mu, okay? And that is the expected number of events that happened in this particular region, okay? So then it will be this is the Poisson distribution happen at ith row, jth column. Is that right? It's the expected, or it's the exponential of negative mu ij times mu ij to the power of nij. That's what we observe, the number of frequencies, divided by the nij factorial. But what are these? So these are the products over all the columns. That's products over all the rows. Okay, so we have this, so that means we have I rows, j columns. Okay, so that is the product over all the I times j numbers. Okay, and this is a joint distribution. Okay, this is a joint distribution of observing all these I times j numbers given the parameters mu. Okay, so here you may ask why I use these boldface letters. Okay, because these are not a number. This is a vector. Okay, that means it's more than one number. Okay, so here that means we have that mu is equals to what? Is actually a vector with how many terms? I times j terms. Is that right? Mu 1, 1, mu 1, 2 to what? To the mu I time ij. Is that right? So that's a vector. Okay. And what is the n? Also with both. And this one is also a vector. Okay. So here, this n is not the total sample size. And this is a boldface n. It's also a vector. It's a vector for what? N11, N12, n13 to the nij. Okay, so if you are from the math department, I think then you should very easily to understand that. Otherwise, just keep in mind, if I change to the boldface, that means it's not a scalar, it's a vector. Okay, it has more than one numbers. Okay, so here the joint distribution is the product for each cell probability. Okay. Mm. So when the total sample size n is fixed, okay, so if n is not random, if n is fixed, total sample size, then it's not a Poisson anymore. It's what? It's a multinomial. Why it's a multinomial? Multinomial means the total is there, is already predetermined. Okay, then how many categories we have? We have I times j categories. Is that right? I means the number of rows, j means the number of columns. Okay, so this follows a multinomial distribution. Okay, so this is the joint probability. And you may say, wait a minute, this is seems like it's different from what we learned in the chapter 1. But if you write it out, you will see this is exactly the same. Okay, this is exactly the same. Okay, so in chapter 1, we have the multinomial, which is this one. Okay, the one that I highlighted here. If you compare this one with the one here, and you will see it's the same. It's exactly the same. Okay. So in this one, it's just the C, the number of categories equals to the number of rows times the number of columns. Okay, so that's the connection between this formula to this one. Okay. 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 So sometimes the row and the column sums are fixed ahead of time. So then we will have the product multinomial samplings. Okay. So for fixed rows, so then we can have, then there are j counts adding to the ni plus. So that means if the row sum is fixed, then for each row, the distribution for the column variables, right, which has j class, okay, follows a multinomial, right? But since we have I levels of rows, we have I rows, is that right? So then these I independent multinomials, then we have I independent multinomials. Does that make sense? So the joint probability of what we observed is the product of these I multinomials. Does that make sense? So just check this one. Here. We know that the number of subjects that had adverse event in the treatment group, it follows a binomial. Is that right? And what about the number of placebo subject that has adverse event. It also follows a binomial. Is that right? And these two binomial processes are what? Independent. Does that make sense? Because these two groups, treatment and placebos, these are independent. Okay, so what is the joint probability of observing these four numbers? Still remember what is the joint probability means? Joint probability means it depends on not one variable, but more than one, right? Okay, so what is the chance of observing 5 AE yes in the treatment group, 45 AE no in the treatment group, 19 AE yes for the placebo group, and 31 no AE for the placebo group. So what is the chance of observing all these four numbers? Then this should be what? Should be a product of two independent binomial processes. Is that right? And you may ask, so what are the relationship between these two binomials? Okay, one process is in the first row for the treatment group, and one is for the placebo group. Will they have the same parameters? Of course not. Why? Because you can easily see that as I said, let's just say the AE yes is success rate. So which group has higher success rate? Of course, placebo group has higher success rate, right? You can see about 38% placebo group has adverse event, but only 10% in the treatment has adverse. So you can so it's easily to see that the parameter P in the binomial, the parameter pi in the binomial for this treatment group and the placebo group are different, right? So we need to have different parameters. You see that? So then these two, to find out the joint probability, you need to have a product of these two binomial processes. Okay, so that is what it means here. So we need to have a product multinomial sampling. And the reason is now changed to multinomial is, as I said, binomial is a special case of multinomial. Okay, always a special case. So you can actually treat the binomial just as a multinomial with the number of category is 2 because the formula is the same. Okay, so this is the Poisson binomial and the multinomial sampling design. I hope you can understand that because these are very important. In practice, if you see a table, you have to find out the design of the sampling first. Then you will decide which probability, which distribution you should use. Poisson, multinomial, binomial, or what? Right? Then you should conduct the analysis using the right numbers. Okay. Okay. Let's see this. This is the seat belt example. So the highway department studied the relationship between the seat belt use. We have two levels: use the seat belt or not, and the fatality. So that's the fatal or non-fatal accident or car crash. Okay, at a certain place in Massachusetts. Okay, so the data should look like that. The seat belt use yes and no, and for the fatality crash, non-fatality crash. Okay, so now let's see. And you may ask why I didn't put the numbers, because I will show you some different designs. Okay, so we could analyze the data as they arise naturally in the next year. Okay, so we keep this table. Now this time, we will apply this table to 2025, year 2025. Okay, so what we do is we just monitor all the car crash at this location in 2025. Okay, every time happened, we just check the driver using the seat belt or not, and then check the car crash is fatal or not fatal. Then I will just put a number here. Okay, I do that. I collect data over through this whole year, and at the end, by the end of year 2025, now I will have a table, and this one will be what? Which design we will have? We'll have fixed row, fixed column, fixed total, or this one. Of course, it's this one. Because the n is what? The total n is random. Because we don't know the total number of car crash we will have. Is that right? We cannot tell how many car crash we will have in 2025 because it's not happened yet. Okay, so then in this case, we should use a Poisson distribution. Okay, with the appropriate parameters. Okay. Okay, the next one is, now this time, I'm not analyzing the year 2025. I'm analyzing the 2024 data. Now we have all the 2024 data collected, right? So what we can do is we just randomly picked 200 records sampled from last year's crash. Last year's crash is more than 200. Okay, let's say 10,000. We cannot analyze all of them. Just randomly choose 200. But this 200 is predetermined, it's fixed. Okay, so then this goes to what? This goes to the fixed total sample size. Does that make sense? Because we've chosen the 200, which is the total sample size is fixed. Okay, then this one follows a multinomial with I times j category. Does that make sense? So this situation gives you the multinomial. Okay, now this one, we can also sample still from 2024. We have all the data. But instead of just choose 200 randomly, now this time I choose 100 fatal crash and a 100 non-fatal crash. Okay, and then for this 100 fatal crash and 100 non-fatal crash, we check the driver using the seat belt or not. Okay, so in that case, which one we should goes to? Okay, check the table, then go to this. It's the fixed column sum. Is that right? So the column sum is fixed. Then for each column, the distribution of X or the distribution of the number of seat belt user that follows a multinomial, or in this case, binomial. Is that clear? So here, then the numbers of people that use the seatbelt for the condition on the fatality crash, that follows a binomial. And this one also follows a binomial. But they have different parameters. Very obvious, right? Because you can easily think about, so the probability of having the seatbelt used for the fatality crash will be much smaller than this one, right? Because using the seatbelt save lives, right? Okay, so this just gives you some idea. And the last one is, how about a design experiment? Okay, then what distribution is. But here, you see that in this case, we cannot have a design experiment because it's not ethical, right? How can we assign the subjects into the cars not using the seat belt and the seat and to see that? Okay, so in this case, this is not a valid approach. Okay, but in some case we can do that. Okay, so that's this example. Any questions so far? Correctly identify the design is the key, is the first step and the most important step to conduct the data analysis. Okay, so the study designs can be grouped into different types. So first is the observational study. So what is an observational study? Observational study is usually like the survey. That's an observational study. Observe, but not control. Okay, so the investigator has no control over the subject group, but only observe it. Okay, so the conclusion from using an observational study analysis doesn't give you the cause and effect inference, but it only tells you the association. Okay, so that's the observational study. And you may ask why? Because there are so many confounders that you didn't control, right? So if you want to have a cause and effect inference or conclusions, then you should think about using the experiment study. So in that way, the investigator has a control over the subject group. Okay, so for the well-designed experiment study, the researcher can make the cause and effect conclusions. Okay, can find out the cause and effects inference. Okay, the next one is the cross-sectional study. So this one is a snapshot of a population or a sample of individuals at a particular time point. Okay, so this is a type of observational study. Okay, and the good thing for this cross-sectional study is that it is very quick. It's just a snapshot. You don't have to wait. It's very cost effective. Okay, and that usually relates to fixed total. And prospective study is to identify a group of subjects and follow them over time to monitor and record specific outcomes, events, or changes. So the prospective study is identify the group and then look into the future. Okay, but this is the most expensive study design. It's not just expensive in the money wise, it also expensive in terms of the time because you have to wait for a long enough time to see the effects. Okay, so that's usually related to the ROSA. So here, these things that I put here, it may not be the truth. Why? You have to use it with cautions because it really depends on how do you define the row variable, how do you define this column variable. Okay, but if you understand all what I said here, you can easily find that out. Okay, so don't just memorize it, but you have to know the way that you so this thinking process, you understand it and then use it. Okay, don't memorize it. And the retrospective study is the opposite for the prospective study. Okay, it works backward in time to examine the historic data or the existing database to draw the conclusions about the associations or the outcomes or cause relationships. So that's the look into the past. Okay, so this is efficient and cost effective. Okay, so let's see a case control study. So in this study, we have 709 lung cancer patients admitted in 20 hospitals in London, and we have 709 age and gender matched lung cancer patients. Okay, so these are all the 709 cancer patients from 20 hospitals, and these are the matched control subjects. And you may ask why we need to do that. Because that can remove lots of confounding effects from different factors that we missed. Okay, so here we only consider their smoking status. Okay, so they are smoker or not. But besides the smoking status, that can affect the lung cancer, like the age and gender, they can also affect the rate of having the lung cancer. Is that right? So to have a matched control subjects, we can remove these age and gender effects. Okay, so that's the main purpose. And then we ask these patients smoking behaviors. So this is a retrospective study, right? Why? Because we look back in the time to see their smoking behavior. Just ask them, did you smoke uh, uh, in the past few years, or you didn't smoke, right? So you ask them, you check their smoking status in the past. Okay, you know their cancer status. Okay, and then you go back. So this is a retrospective. So you can see it's uh, cost efficient, right? What about a prospective study? For the prospective study, maybe is, let's say we have 709 smokers and 709, let's say, non-smokers. Okay, and then we just follow them. Maybe in 20 years. Okay, of course, some of the patients may pass away, but we will just record their they have a lung cancer or not. Okay, and then we will do this analysis. So here, this is a prospective because we look into the future to see they will have a lung cancer or not. But we know their smoking status. Okay, so that will be a prospective. But here, this one will be a retrospective. Okay, so we can, since this is a retrospective study, we can directly estimate what? Can we estimate as a smoker, what is the chance of having the lung cancer? So given the smoker, so what is the chance of having the cancer? Okay, C stands for cancer, S stands for smoker. So the probability of having a lung cancer given among the smokers, can we estimate this one from here? No, we cannot. Why? Because this is column fixed. Okay, so for column fixed, what can we estimate? We can estimate is the probability of what? Of being a smoker among lung cancer patients, right? Or the probability of having a non-smoker given the among the cancer, or being the probability of being a smoker among the non-cancer, or the probability of being the non-smoker given the non-cancer. So for these, we can estimate. For all these, we can estimate, but we cannot estimate that because this is column fixed. Is that right? Okay, so make sure you understand that. Okay, so the next question is, are we really interested in this in practice? So in practice, if we want to see the smoking effect on the lung cancer, so which is a more useful estimate? The probability of being a smoker given the lung cancer, or the probability of getting a lung cancer among. This one is more useful, right? We should estimate among the smokers the probability of getting the lung cancer. Then we can compare with what? The probability of getting the lung cancer among the non-smokers, right? If we can estimate these two and we have and we see the big difference, then that is a very solid evidence to show the smoking effect. Is that right? Because if this one is much higher than this one, then we can say, well, you see that the chance of getting the lung cancer among the smoker is, let's say, 10 times higher than the chance of getting the lung cancer among the non-smoker. So that's very useful statement, very uh, easily understand statement, right? So this is more useful. But somehow we cannot estimate that because of the design of the study. Okay, so the question is, if we design in this way, is there a way that can help us to estimate that? Although we can only estimate this, but is it possible we can still estimate that? Yes, but we need more information. What information? You will see that in the next. So that's the Bayes theorem. Okay, so the great thing for the Bayes theorem is what? Okay, these it cover it builds a connection between these two conditional probabilities. You see that? That's the beauty for the Bayes theorem. Okay, so the probability of A given B is directly related to the probability of B given A. You see that? Okay, so in this case, let's say the A is cancer and B is smoker. Okay, so A is cancer status, lung cancer status, and the B is smoker or not. Okay, so let's say B is smoker, A is lung cancer. Okay, so directly from the table. Okay, so what we can do is we can estimate this one through this. This we can estimate, right? So the probability of being a cancer among the smokers is equivalent to what? Based on the Bayes theorem, is the probability of a smoker given the cancer. That we can directly estimate from that table, right? So given the lung cancer, the chance, the proportion of the subjects that are smokers is 688 divided by 709, right? That can be estimated. So we need more information, is multiplied by the marginal probability of cancer. And this is not the marginal from here. No, these marginal are useless. But this is the prevalence of having the lung cancer in the population of the study. Okay, since this study is conducted in London, right? So I assume the population should be the adults in London, okay? So then we should know for all the adults in London, what is the prevalence, what is the proportion of adults in London that are smokers? Okay, so that is the P cancer. That's the PA, right? Divided by the P smoker. That's the prevalence or the proportion of the adults in London that they are smokers. Okay, so these two information we need to get from the population. Okay, so if we don't know, we can just try to have a good estimate using like the historic data. Okay, so if we can do that, then we can get the probability of getting the lung cancer among the smokers. We can. Okay, but with these two pieces of extra information. And similarly, now we can have the probability of getting the cancer among the non-smokers is this one, right? Okay. So for this one, we also need to get that, and these are the same, right? So after we get these, then we can compare these two numbers, and that difference shows the smoking effect on the lung cancer. Okay, so this gives you a possible approach to estimate the proportion, the proportion of the lung cancers among the smokers or among the non-smokers, which cannot be directly estimated from the table, but through the Bayes theorem. Okay. 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 I think we are running out of time. So, any questions before we stop? Work on the homework one, and let me know if you have any questions. And read the chapter 2 materials, and I will try to go faster. Start from next time. I think we've already behind the schedule, but I think it's worth to spend some time to talk about those basic concepts. So start from next time. I will try to be quick. Yeah. Any question?
Yeah, I have a question. Concerning the assignment, are we to write it with our pen or we should write it on documents, like type on it?
Yeah, type.
Oh, we should
But
type.
if
All
you
right, thank you.
write, you scan it and
Okay,
send it. That's also fine. And
all right, thank you.
acceptable format are the PDF, Word file, HTML, these. Yeah.
All right, thank you.
Okay. If you have no question, let's stop.